Hello and welcome to Learn ADS in 5 minutes. This is tutorial 39 on two-tone nonlinear analysis using harmonic balance simulator in ADS. Now just a word of caution, this video won't finish in 5 minutes because we do have quite a bit of material to cover, but I will try to make sure it's worth every minute you spend on this video, so stay tuned. What you will learn in next few minutes, how to set up harmonic balance simulations to perform certain efficiency calculation. So this topic is continuation from our last tutorial where we learned how to set up and run one-tone harmonic balance simulation and power sweep analysis. Then we will look at how to set up and run a two-tone harmonic balance analysis and then perform related measurements such as IMD products to look at IM3, IM5 or sometimes interchangeably it's called as IP3, IP5, and so on. We will also learn to use some mixed tables and then use measurement functions for performing some of these intermodulation product calculation, both in a schematic, but more so in data display, because sometime when you forget, you could do a lot of post processing without rerunning the simulation. So we will talk about some of these. Now, before we get started, as always, subscribe to my channel. If you have already subscribed, click on the bell icon to enable all the notification. And if you like the video, then don't forget to hit the like button and click the share icon to share it with your friends and colleagues who may be interested in watching similar tutorial. Now, let's get started and go over each of these topics one by one. Now, when we talk about the last example we were working in the last tutorial video, we set up a harmonic balance. We ran a one-tone simulation and look at the power sweep curves and all that. Now let's talk about efficiency. Now, more commonly, there are two types of efficiencies, which usually, especially amplifier designers refer to. The more accurate one or the more common one, which is used widely across the designers community, is power added efficiency. And that's given by this formula. That means we need to compute the output power minus the input power. So that essentially means gain and divide by PDC, that's the DC power consumed in our amplifier, and multiply by 100, you get a percentage efficiency. The another efficiency, which people also use sometimes, is called drain efficiency or DC to RF efficiency. And here, the simple formula is output power divided by the DC power consumed, and you multiply by 100. Now, in terms of accuracy or usefulness, the PAE is a more accurate representation of the circuit performance matrix. So we always, prefer using PAE. But in some cases, if you just want to look at DC-RF, you can go ahead and do those measurements in ADS. Now, the important thing to consider while using PAE into your circuit, you need to compute power at three places. Right? And the way we compute power in ADS is by simply giving a voltage node name and putting a current probe. So you can see I have at the input a voltage node name, wire label V in, and I have connected a current probe and I named it as I in. So that would help us to compute P in. And similarly at the output, as you saw earlier, we have the V out and the I out. This will help us to do P out calculation. Now at the DC bias line, I have connected a DC, current probe, and I named it IDC and give a wire label VDC. So this will help us to do PDC calculation. Now with these things in place, if we go to simulation HB template and look at the measurement functions here, we do have DC to RF function. And here in DC to RF function, the syntax is kind of pretty straightforward. But in case you have some confusion referring to that, double click and open a help document. And this help page kind of explains the syntax and the related details. So the simple thing to remember here, for every voltage, you have two nodes, V plus and V minus. Similarly, for VDC, you have V plus and V minus. And then you have I probe in the same order as the voltage node. So in this case, we do have, current RF, which is the current probe for the output, and the IDC. And harmonic frequency index simply meaning at what frequency would you like to do this calculation. So here in this case, the syntax, and I already have the function placed here, and you can see the syntax V out 0 because 0 we are working at the single ended kind of amplifier. If you had a differential amplifier, you can define V plus and V minus. And then we have VDC, then I out dot I, which is the output or RF current probe. And then we have IDC, which is the DC current probe. And index 1 means we want to do calculation on the fundamental index. Similarly, for PAE, remember the formula is P out minus P in divided by PDC. So basically, we need all three inputs here. So we have V out, V in, and VDC. And the same order, you have I out, I in, and IDC. And index 1 simply means the index of fundamental at the input to compute P in, and index 1 of the output to compute P out, and 1 simply means fundamental. But in case you're using this function and you're designing frequency multiplier, your input index can be 1 and the output index can be 2 or 3 or 5 depending upon what kind of frequency multiplier you might be designing. Now with these two things set up, and we already have a power sweep set up in harmonic balance, we go ahead and run simulation, and here we can notice the efficiency plot. So blue curve is representing PAE, and the red curve you can see it's DC to RF efficiency. And beyond a point, you have these two curves start to disagree with each other, because once your amplifier going into CDS compression, you can see PAE drops, and purely because of formula, remember the numerator is gain, P out minus P in divided by PDC, whereas DC to RF still keeps rising to that point and shows a slight dip. And these things are little amplified because they are all multiplied by 100 index. So what you see here is kind of little bit of amplified performance. But that's how easy it is to do efficiency measurements for your amplifier or active devices. Now let's go back to understand how can we do two-tone setup, and the concept is again very simple. The only difference here is basically two. So one, instead of P1 tone, if we go back to sources frequency domain, which we talked about during last tutorial, instead of using this P1 tone, we use PN tone. And once we have N tone, so let me place it to show you how it comes out. Notice the square bracket, and that's representing index. That means we can have as many frequency tones we want to feed into a circuit or a system. Now for each frequency tone, you have corresponding power to be defined. So if I double click on this source here, and we can go ahead and add, let's say 3 tones or 4 tones or 5 tones to our source, and we can specify the frequency as we need. Now for each of these frequency tones, we exactly need to have the power defined. Otherwise, ADS don't know what power level to set for those spectral content which you added just now. So that's how we set up PN tone source. Simple, isn't it? Right, so once we have the PN tone source here, I have defined two frequencies, FC minus F offset, which is basically the lower side tone, and FC plus offset, which is higher side of a tone. And in the variable, I have defined my FC as 5 gigahertz and F offset as 1 megahertz. So basically, it will be 4.999 gigahertz as a lower tone and 5.001 gigahertz as the upper tone. Now, once we have this basic setup done, we set up harmonic balance, and in here, instead of just having one frequency, we need to define the frequency in the same syntax as we did in the source. So here we have FC minus offset and FC plus offset. Now each of these tones, we define the order, which is the number of harmonics we want to consider for individual tones. Now in my case, I have 5 harmonics for each tone. That means if for the intermodulation product, the maximum order which can get generated is 10, which is 5 plus 5. So as you understand from theory, the intermodulation products will be denoted by a formula MF1 plus minus NF2. And where F1 and F2 are the two tones we are feeding to our circuit, M and N are index, which is nothing but these order index. So here for my analysis, I have set the maximum mixing order, which I want to see in my results 7, although I could have gone till 10. But for any practical purpose, there's no fun, for more than, seventh order product, to be very frank, because these products itself are far from our, carrier frequencies or the main tones, and anything beyond that can be easily filtered out, and they are pretty small in power anyways. Right, so with this basic setup, rest everything is okay. We can go ahead and run simulation. So when we look at V out plot, you will end up seeing this kind of spectrum. And you can see multiple tones, and the intermodulation products are so closely spaced that you could only see multiple arrows. So if you use this zoom graph function and zoom around the fundamental frequency area, and if you zoom 2-3 times, you would start to see these tones and the intermodulation products which got generated. So here these are two fundamental tones which we fed, and these are the IMD products which got generated. And basically just by looking at it, it's the third order product, it's the fifth order product, and this the seventh order product. However, you can do more you know uh, proper measurements as we would see here. So here in my case, I have markers set for these third order products, and we can see the levels of these. And similarly, we can put this M2 here, and we can do DBC, kind of calculation to see how many dB down is our third and fifth order product. Along with this, anyway, like earlier, we are also seeing this parameter response. Now, another interesting thing, because now you are producing so many frequency content, is to keep track of which are these frequency content, due to which source combination they got generated, what is their intermodulation order, and things like that. So that job is simplified by looking at this mix table. And the way we plot this is by just inserting a table and selecting mix from the available measurements, and that's how you end up getting this table. Now, what is represented in this table is all the frequency content which you have at the node V out, because this is what we are plotting. And here mix 1 is representing the lower side tone, and mix 2 is representing the higher side tone. These are the two frequency contents. And if you look at 4.999 gigahertz, if you read the harmonic index number 1, 0, that means it's only referring to this tone because this is multiplied by 0. So this is the frequency content here. Similarly, 5.001 is 01, which is representing this side. Now, if you refer to 4.997 and 5.003, and look at this mixing product is 2 minus 1. That means this product is getting generated because of the second harmonic of this tone minus the fundamental of this upper tone, and that's what is producing. And same way, if you look at 5.003 is minus 1, 2. That means second harmonic of higher tone minus the fundamental of this product is basically generating this M2 product. So that's how useful is this mix table. Now, how do we do IP3 and IP5 or IP2 kind of measurements using two-tone? Well, for that, like we had functions for efficiency and all that. If you go to simulation harmonic balance library template, there we would find IP3 input, IP3 output, and a generic IPn, right? Because IP3 is very commonly referred. That's why you directly have a function to compute those. But IPn, N can be defined by you. It can be second order product, fifth order, seventh order, ninth order, whatever you want. Now the syntax here is very simple. V out is the node at which you want to do measurement. 1, 0 or 0, 1 determines whether you are doing measurement with respect to the lower side tone or the upper side tone. And we just saw that in our mix table. And 2 minus 1 or minus 1 2 or whatever is your intermodulation product mixing content or mixing index, that's what described here. So by using this index, it knows the carrier. By using this index, it knows where is your intermodulation product, and then that's how it calculates the intermodulation product. And this is kind of representative picture. If you see, how do we compute these IM products? So if you take a linear gain slope of the fundamental and keep extending it to infinity, for example, and then if you take the corresponding intermodulation or product like third harmonic or the second harmonic, and if you again take this linear slope, wherever they intersect, and if you look at the y-axis, that's where you get the IP, magnitude. So IP2, because it's a second harmonic, rises at a lower slope compared to the third harmonic. When you compare IP2, you will see higher number because it will intersect farther away from the third order product, which has a higher slope. So it will intersect much quicker. We will see all that, but this is how the syntax is. And that's how I have set up three measurement variables here. And here you have IP3 out, one for the lower side. So here I'm considering the lower side tone and the lower side, intermodulation product. Here I'm considering 0, 1, which is representing the upper side tone. And then I'm talking about 5.003 gigahertz, and 50 is the reference impedance basically. And again, if you're confused, double click on the help. It will open up the documentation page and you can refer what it is and how it does the measurement. All right. Now remember, all these measurements are only valid if your amplifier is operated and the input power is when your amplifier is in linear range, right? So by activating this, let's run the simulation and open the next page. And here you can notice I have these things plotted in a table. OIP3 lower is 31 dBm. OIP3 upper is around 31.1 dBm. So almost the same, IP3, because if you compare the magnitude or the amplitude of these two tones, they're almost the same. Now in a low power amplifier or LNA or medium power amplifier, this is kind of true. But if you're dealing with high power amplifiers such as SSPAs and 50 watt or 20 watt kind of amplifiers, if your amplifier has a memory problem, then you will have these two amplitudes which may not be same. Again, it depends whether your amplifier does have a memory problem or not. Okay, so in this case, it's kind of same. Same thing, what we did in a schematic, the same equation, if you want, you could write even in the data display, because this allows you to do post-processing on the spot. Because if I want to see fifth order product, seventh order, and all that, I can just use the data which is already available with me from the simulation, and it's exactly the same equation. So you can go to schematic, just copy paste this equation into data display like what I have done here, and it will straight away work. Just make sure this name here is not same as your schematic. Otherwise, ADS don't know which one are you going to plot. Okay, so with data display, here is the DD, which represents data display. You have the same number here. Right, in IPN, here you can see I have used index 2. That means I want to do second order intercept point. And here you can see the number is higher than the third order intercept point for the reason I just explained. Now, this is all what it takes to do a two-lone, simulation setup and run the different kind of measurements characterizing your circuit's performance. Now, one last thing I would like to see, because this is like a big mix table, but sometimes I only want to see the contents which are around my main tones. But this kind of table is kind of pretty big. So if you go through this table, it has a lot of frequency content, and sometimes I don't want to see all of them. So here I have a way where I place two markers on the tones, and anything in between these two tone markers will be captured by this mix table. And again, I already talked about some of these in my data processing tutorial. If you haven't watched that, you can go ahead and watch. So here I'm just declaring a variable, finding the index at M3 marker, and put another variable finding the index at M4 marker, instead of plotting the entire mix. Because if you remember, if you look at mix, look at the variable info, it is 49 frequency points, because those are the number of content of frequency contents got generated after harmonic balance. So I just put a square bracket and read any index or any frequencies starting from this index where my marker 3 is placed, going up to point where my marker M4 is placed. So if I just take it out for clarity purpose and then expand it, you can see there's nothing. There's only 4 frequency content, 1, 2, 3, 4. But if I take this marker and put it extreme, you can see now I have more frequency content, which I can see. So nothing major, but something which will, kind of make your job much easier, not to go through this big table, and you can just focus on what you want. Well, that's all for this video. Thanks for watching till the end, and hopefully the content presented here will be useful for your circuit analysis job, and you would be able to easily run two-tone analysis. Again, don't forget to subscribe to my channel and give it a thumbs up if you like the content presented. See you in next tutorial video. Thanks for your time.